optimization problems. And this is tons of applications all over the place trying to find a maximum or a minimum. And calculus helps us with that so much because whenever we have a maximum or a minimum, the slope of our tangent line is going to be 0. So no matter where you on a graph you have a maximum or minimum, your slope of your tangent line is equal to 0. So if you're asked to find a maximum of a certain type of function, you could take the derivative, set the derivative equal to 0, and then answer the question. Do you remember solving max-min problems in grade 11?
Yeah, they're so hard.
Okay, they were so hard in grade 11 because they were parabolas and there's a formula for the axis of symmetry. I don't know if you ever learned that or ever seen that.
I didn't even know until this year. I didn't even know there was a formula. So just intuitive.
It is intuitive, but yeah, you used to have to complete the square to find the vertex. Okay? Now we're going to look at that same type of question. A ball is thrown vertically upwards at time t seconds after its height in meters is given by this formula. Calculate the time at which the ball is a maximum height and find the value of y at that time. So in grade 11, you would have had to complete the square. And now, what we're going to do instead of complete, you want to complete the square just for old time's sake? You want to see if you remember it? You don't even want to? You don't even want to see it? Okay. So now, the derivative of this one, 15 minus 2t. Set that equal to 0, and you can solve for t. We'll be at 7.5.
Why didn't you teach us this to begin with?
Well, this is how mathematics works. We find out one way to do something. It's often complicated. It takes time. And as you become more advanced, you find out something that makes your previous work so much easier. Right? Think about 100 years ago. I want to send a short message to somebody across the ocean.
Internet, SMS.
Right? Then I would have to, well, I don't even know if telegraphs would have existed. I would have had to write it down, find someone to put it on a ship, find someone to deliver it when they got on that ship, and it's not that. 100 years ago? Yeah, it's true. It's World War I. So we could do that. 200 years ago, you'd have to send it on a ship. 20 years ago, 20 years ago, you could send an email. 1998, you could send an email in 1998. When in 1997 is when I was in South America. Yeah, I'm recording this. Oh well. Here, I'll pause it. All right. So now that we've found the time, in order to find the value of y, well, now you can substitute that time back into the equation. You want to check? Can someone check my math? This was a typical grade 11 question. Fred wants to enclose a rectangular parking lot with 60 meters of fence. Okay? You used to hate these questions. There's a building on one side of the lot. So here we have our building, right? And here's our parking lot. And this is so logical in that it makes sense to put a fence completely around the parking lot so nobody can get in. Or if you build it during work hours, nobody can get out. Have it. So Fred has 60 meters of fence. There's a building on one side, so no fence is required there. Find the maximum area that Fred can enclose. So in grade 11, you would have had this question, and the hardest part was setting things up so that you could make an equation. Now, in this rectangle, this side and this side would be the same, and this side would be different. So sometimes people start this way. Now, since you have 60 meters in total, you want to create something so that it's all in one variable. And you would say, well, if I had 60 meters in total, and I've used up x here, and I've used up x here, I'd have 60 minus 2x left. And the area that I have, length times width, would be 60 minus 2x times x, or 60x minus 2x squared. Now, once you create that equation, again, in grade 11, you would have had to complete the square to find that maximum. Now, all we need to do is find our derivative, set it equal to 0, and solve. And x is equal to 15. So our actual measurements, if we put them in here on green, are 15, 15, and 30. And if you've done enough of these like I have, you've noticed the pattern over the years that this is always half of what you started with, and these are always half of that. That's always the case, because what you could do, right, we could prove it with calculus. Okay? You now, well, that's a good thing to do. So I just said a pattern that you notice. How do you prove that with calculus? So I'm going to take, well, I'm going to keep that x there. I'm going to take this away and make this p minus 2x, right? So now any perimeter that you have. So our area would be px minus 2x squared. And if you set it, if you find your derivative is going to be p minus 4x. And when solving for x, you will always get 1/4 of p, which is always, and this here will always turn out to be half p. So you can prove it very simply with calculus. Well, I try not to tell you that trick in grade 11 so you don't do them all the time. Like, oh, I know Mr. JR told me that we have 80 meters of fencing, so it's going to be 20, 20, and 40. And then you don't have any work to do, and I can't test you if you know how to complete the square. Right? Or I create sections in there so that you can't do the same thing. Right?
That makes it harder for these kids who don't actually know the trick, though.
Right, maybe. So we've got some problems with learning a trick.
Let's actually do a trick to know.
And this is a question from grade 12. You might remember doing this question last year. Rectangular sheet of cardboard, 10 centimeters by 7 centimeters. So here's our cardboard. It's 10 centimeters here, 7 centimeters there. Corners are cut. Small squares are cut out of the corners. You remember this in grade 12? Small squares are cut out of the corners, and we want to find the maximum volume of the box. So we would call this x. This side here would be 10 minus 2x. This side here would be 7 minus 2x. And if you folded the sides up, you would get an equation for the volume. Length times width times height. And last year you would have taken this equation. You could draw a quick sketch of this equation because it's in factored form. You would know that you have an x-intercept at 0, from this one, x-intercept at 3.5 from this one, and an x-intercept of 5 from this one.
3.5 then. Because having cutting 5 from both sides would give you a negative.
And if you think about the overall power here, this would be an x cubed. And so our overall graph, you would have known the shape looked like this. And last year we were required to use our calculator to find that maximum. In this case, we're probably still going to need our calculator because the value isn't very nice, but we're going to see how calculus could help us get there. You remember this one, right? So we needed our graphing calculator. Yeah, we cut out the paper. Now, if we want to use calculus, we're going to need to multiply this out. So first I'm going to multiply the x in there, and then expand this completely. So I'm going to get 4x cubed, and here we'd have negative 20x squared minus 14x squared, negative 34x squared. For our x's, we're going to have plus 70x. So multiplied it out, and now we can find our derivative. And we get 12x squared minus 68x plus 70. So before we needed a graphing calculator. We're going to see if now we can solve this without a graphing calculator. Well, if I set this equal to 0, I can factor out a 2. And now we have a very wonderful thing to try and factor. Okay? Just scroll up a touch, yes.
Pretty big number.
Those are big numbers.
We can iterate through them.
Okay? Unfortunately, it doesn't factor.
That'd be so trash if you went through all the try and go.
No, you can do
All the different types. So then, if you wanted to solve for x, you would have to go to your quadratic formula. So it's going to be negative b plus or minus b squared minus 4 times a times c over 2a, which is 2 times 6, 12. And plugging that value in and figuring out. You could use now a regular scientific calculator. It's not by any means. You could still do some parts by hand, right?
What if it asks for just leave it like that? If there's non-calculator and you want an exact answer.
You could leave it. You could leave. Well, they'd ask you to simplify this. That would be the thing you would want to check. But here in this case, 34 squared is larger than 24 times 35. And you would work from here. So last in grade 12, you would have gone to your graphing calculator, find that maximum. That's still a faster way than what we're doing.
What if the minus sign gives you an extraneous root? Like if the square root is bigger than 34?
If the square root, then there would be no solution, right? But we know that this one has a solution.
Plus or minus, you have to check.
Well, the other thing about the plus or minus, you have to be the x value that you get. There might be more than one answer here, but what we're looking for is what makes sense within the scope of the question. Okay? And in the scope of the question, and that's why I drew the graph here, only a value of x between 0 and 3.5 makes sense. Because if you cut out anything larger than 3.5, okay, if you do that, you're not going to get any cardboard left to fold up. The reason that there are two answers that show up is because your calculus doesn't care about the context of the problem. It's going to find this maximum and this minimum, even though that minimum makes no sense whatsoever. Right? That would have a negative volume. Right? Try to imagine that.
Gives you space, not
Just gives you space. I've got a carton of milk with a negative volume of. Try to. So if we did go to our calculator, we could find the maximum. If we applied this and found the values of x, one of those values of x will be between 0 and 3.5. The other value of x will be between 3.5 and 5. We could take out our calculator and do those calculations and find it exactly. Plug it back into your original equation to find the actual volume. But we're not going to do that right now. You can do that on your own.
already did.
You did it? It worked?
I think so. I'm not sure though. Theoretically, it should work.
So the hardest part in these questions is setting them up. So here, you've got a right-angled triangle ABC. The lengths AB and BC will always vary so that the sum is 6. So it could be 2 and 4, 3 and 3, 5 and 1. And as they vary, the area of that triangle is going to change. So what I want you to do is figure out if AB is x, how would you write BC in terms of x? So we're going to want to try and always write things in the same, yeah, exactly, with the same variable. Then if you have that, what would an expression of our area be, and what would the maximum area be? All right, how did you do? Did you get your area formula to look like that? Now, multiplying things out, you're going to get 6x minus x squared all over 2. I'll write that out. Which is the same as 3x minus 1/2 x squared. See how I undid adding fractions?
Good job.
Okay. And now we can find our derivative, set it equal to 0. And this isn't a very exciting result because you might have predicted that if both sides were the same, you would get the biggest area. And that is true.
If you just took the straight derivative and then plugged it back to the original equation, was that
I can do that in my head. I cannot do that.
What do you mean take the straight derivative?
So instead of setting up the area, I know that you take the derivative and those are either minimum or maximum. Right? 'Cause
Derivative of what, though?
derivative of the expression we created, which was
What is the area expression? Right, if you're wanting to find a maximum or minimum of area, you need to have an area equation for that. So then the maximum area, okay, we haven't answered the question. Find the maximum area. If the side is 3 and the other side is 3 divided by 2, our maximum area will be 4.5. Was there any units here? Centimeters squared. It did ask us for the maximum area, so then once you find your value of x that gives you that maximum, then you can plug it in. All right, let's do a little bit more of an advanced question here. Yes. A closed right circular cylinder, base radius r and height volume and height h has a volume of 54 pi centimeters cubed. Now, I don't know if you have ever bought a drink and instead of saying 700 mils, it says 65 pi mils, but that's the case in this example. They're telling us that the volume is 54 pi. Everybody okay with converting centimeters cubed to milliliters?
Yeah.
1 centimeter cubed is 1 mil. So this is 54 pi mils. You like, maybe you should get into,
Not really 1 minute. It's only like if it's a water.
well, it's only if it's water, that is true. But it's a general,
It's a drink of water, okay? It's 54 pi milliliters of water.
4 pi milliliter units of water.
there we go.
Thank you.
Find the cylindrical shape.
So given this information, we want to show that the surface area of the cylinder is given by this formula.
Cool.
So one of the things that you're not going to like that I'm about to tell you is you need to know your surface area and volume formulas for a bunch of shapes. Okay, so let's think about a cylinder. You don't know any of them. Well, we're going to have to learn them. Okay. So for volume of a cylinder, volume is whatever the base is, the area of the base times the height. And that's of any kind of shape that has the same thing all the way through, that will be its volume. You can imagine it as if I want to make a cylinder, if I take the area of the bottom, which is like a thin piece of paper, and cut it out, and then keep stacking those thin pieces of paper up, I will fill up the whole thing as a solid stack of paper in that shape, and that would make my volume. For surface area, the surface area of a cylinder with a radius and a height, can you see that your surface area is going to include two circles? One circle's area is pi r squared, two circles' areas will be 2 pi r squared. Now, what is the surface area of the round part around the cylinder? Well, if you think about a cylinder, if you imagine this cylinder that I have right here, and you maybe can visualize this if you've ever had a can of soup at home and peeled off the label. And if you've never peeled off the label, go home tonight, take every can in your parents' pantry and peel off the labels.
And switch them.
You can, it'll be, if you were younger, you might get away with this. Now that you're in grade 12, if you peel off all the labels, it was for school.
It was a calculus project.
It was a calculus project. Well, what happens when you peel that label off?
It's pretty long.
You peel it off, and what shape is it?
Rectangular.
It is just a rectangle. So when a rectangular, yes. So you peel off that label, you get a rectangle. Let's label some things about this rectangle. This is its height, right? And this matches up with all the way around is your circumference. So this part is 2 pi r. So for most of our formulas, if we think about them, we can actually create them. So what is our formula for circumference? It's pi r squared plus 2 pi r times h. Now our job is to show that the surface area of this one is 108 pi over r plus 2 pi r squared. What they're wanting is our formula right now has two variables. Our formula has r and h on the right-hand side. And so that will make it not possible to do the derivative unless we do implicit differentiation, which we're going to not want to do right now. We want to create an equation that has only one variable. In order to do that, we would need another equation where we could solve for h in terms of r and then substitute back in. In this example, the volume of our cylinder is the area of the bottom, pi r squared, times the height. And we know that the volume of our cylinder is 54 pi. So if I want to solve for the height,
Can you divide out pi right away?
you could divide both sides by pi, yes?
Same
And I'll get h by itself by writing r squared over 54. So because I have this information here, I can plug that back into my formula for h. So my surface area, which is 2 pi r squared plus 2 pi r times the height, and now my height I can substitute in r squared over 54. Oops, 54 over r squared got a little bit crazy there. There we go. 54 over r squared. And simplifying this completely, we'll get 108 pi over r, which is what we were asked to show. Okay. The whole reason that part A is getting us to show it this way is now in part B, we can find the radius and the height that makes the surface area a minimum. We're going to talk about why we're going to want to do that in a second. Okay? I can go back for a second. We want a minimum. Anytime you're wanting a minimum of something, in this case, minimum of surface area, you're going to want to take your surface area formula and find its derivative. So finding the derivative, well, I'm going to just rewrite S here, and when I rewrite S, I'm going to rewrite it. Here's the 2 pi r squared plus, it was 108 pi over r. Yeah. Are you okay if I change that r to a -1 to help us do the derivative easier?
No.
And so now we're going to take the derivative 4 pi r minus 108 pi r to the -2. Set that equal to 0. And use our algebra skills to solve this. I'm going to put that r squared back on the bottom. So I can move the 108 pi over r squared to the other side. That r on the bottom, or that r squared on the bottom, is going to cause a problem. So if we multiply both sides by r squared, we get 4 pi r cubed. And the reason why this question was originally given with a volume of 54 pi is because at this point, if you divide both sides by 4 pi, oh, we have pretty numbers.
You do it on purpose?
Yes.
No, accidentally.
I accidentally, like, I'm going to pick a random number for volume. Oh, I haven't used 54 pi in a while. That seems like a good plan. So it works out really nice that r is 3. If we go back to our diagram, that means this value here is 3. And since we know that our height is 54 over r squared, we got our height as 6. Fascinating. Beautiful. So we now figured out that in order to get a minimum, we would need our radius to be 3 and our height to be 6. So Peter asked the wonderful question, why would we like to do that? Okay.
Do we have to write this down? Where are we?
Let's think if we know anything in the shape of a cylinder, a soda pop can. So now we know we want to create a soda pop can with a volume of 355 mils. So we'll change that to cubic centimeters. Okay? Yeah. You can go. Now, if you're making a can of pop to have 355 millimeters, you want to have the surface area to be a minimum so that you don't have to use as much aluminum. The smaller your surface area, the less aluminum you'll have to use, the cheaper it's going to be to make. Let's find out if the can of pop is actually a good shape or if they've screwed up and should change it a bit. Okay? Now, there's different things we would have to consider because, I mean, it's not a perfect cylinder. 355. Okay? So, again, our surface area is 2 pi r squared plus 2 pi r h, and our volume is pi r squared times our height. In this case, our volume is 355, and so our height is 355 over pi r squared. Going back to our surface area, and this is where, in real life, the numbers don't always work out nicely. 2 pi r squared plus 2 pi r times 355 over pi r squared. So the pi's cancel out nicely, right? And our surface area is going to simplify to 2 pi r squared plus 710 r to the minus 1. Actually, some of the numbers look nicer than before. We still have a pi.
Okay, so do you find the radius?
Now we can find the derivative, calculate the radius, calculate the height, and see if things match up nicely. Now, my big question that came to my head that I'm not sure of the answer, but something I noticed in the last question, and this is the problem with liking math and not just being happy with getting the answer, is whenever I solve a question, I ask myself another question which makes me have to do more math. I was like, isn't that interesting that the radius is half? I thought, I wonder if that always happens. The only way to check that is to create another question. And so we're going to see, does it happen with the Coke can? Is the radius half?
That's pretty cool, actually.
Okay. And then if it is half, was that just lucky again? Or how would I then prove it's always half?
Let's prove it afterwards.
So we'll have to just see what happens. So this is where we're at. We find our derivative, 4 pi r minus 710 r to the minus 2. Again, set that equal to 0. And we get 710 over r squared equals 4 pi r. 710 equals 4 pi r cubed. And this is where numbers don't turn out to be nice. So we take 710 and divide by, yes, 4 pi. 56.5. It actually works out to a really cool 56.5, as opposed to a not cool.
0.000004.
I divided both sides by 4 pi.
And it just came out real nice.
Well, it came out to 56.5, 0.00000048. Like really nice 56.5. Not like a mostly nice 56.5, but a really nice 56.5.
4 and an 8. Are you horrible?
And now we could cube root both sides.
No answer?
Peter, no one wants that.
And we get a not very nice 3.84. 3.837. So that is our radius. If we want to find our height, If we want to find our height, we could plug that back into this equation. 355 divided by pi times r squared. Oh.
So are we going to do a proof now?
Well,
No, I believe it's
see, with all the decimal places, it does work out to perfectly double once again.
Okay, so then
So then if you think about your can of pop, though, is it a good design?
well, for one,
Because the diameter should be the same as the height then. But it's longer, isn't it? So maybe they had to take into consideration the curvature of it. But